Hi, and welcome to Lecture 7 on wire delay. In modern CMOS circuits, designed in advanced state-of-the-art technologies, it's not the gate delay that slows down the circuit, it is the interconnect delay. Interconnect, that is the wires connecting blocks on the chip. This slide shows the lecture outline. In the lecture, we are going to look at interconnect modeling, including the wire resistance and the wire capacitance. We look at the wire RC delay and introduce the Elmore delay model to handle wire delay. Chips are mostly made of wires called interconnect. In a stick diagram, wires set the size of the chip. Transistors, they are just little things under the wires, and there are many layers of wires. Wiring is as important as the transistors when it concerns speed, power, and noise. And as we can see to the right, alternating metal layers run orthogonally, with odd metal wires running vertically and even metal wires running horizontally. Until the 180 nanometer generation, most wires were aluminum. However, contemporary processes normally use copper. There have been some problems to develop an appropriate copper technology because copper atoms diffuse into silicon and damage the field effect transistors. Therefore, copper wires must be surrounded by a diffusion layer, as we can see on the little inset figure to the right. In this table, we also have some typical values of the bulk resistivity of a metal in micro-ohm centimeter, like aluminum 2.8 and copper, that's almost a factor of 2 down to 1.7 that we can win by going from aluminum to copper. In the layer stack, the AMS 0.35 micron process that we used for many years, it has 3 metal layers, metal 1 for within cell routing, metal 2 and 3 for vertical and horizontal routing between cells. Modern processes use 10 to 10 plus metal layers. Metal 1, it's thin and narrow. It's for high density wiring in cells. The mid layers, they are thick and wide. They are for global interconnect. And the top layers, they are really thick and wide. And they are for VDD, ground and clock. You can see that wiring is organized in tiers with narrow and thin wires down here. One step up we have wider and thicker wires, and a third tier up here, and then the top layer. Here is an illustration of an interconnect wire. In the old technology, during the 70s and the 80s, wires were rather wide compared to their length. For each new technology, they have become narrower and narrower, while keeping their length because chip size has not decreased. In today's nanoscale technology, wires are quite long and skinny, thereby becoming more and more resistive. For long skinny wires, the wire resistance cannot be neglected. Wire length is increasing with large chips. Wire cross-sectional area shrinks with feature size, so wires can no longer be modeled at capacitances alone. We need a distributed RC model. Now, let's have a closer look at the resistance of the wire. It is given by the well-known relationship between resistivity ρ, wire length L, and cross-sectional area A. The longer the wire, the higher the resistance. The larger the cross-sectional area, the lower the resistance. Of course, wide cables reduce the voltage drop along the cable due to its smaller resistance. Here the area is given by the wire width multiplied by its thickness. So the resistance is equal to ρ times L over W times T. Now all wires in a certain layer has the same thickness, T. Hence, sheet resistivity is a convenient measure. The sheet resistivity Rs is equal to the resistivity divided by wire thickness T, and it's given in ohms per square. The number of squares in the direction of current flow is given by the length divided by the wire width. So we just count the number of squares along the wire to get the total resistance. If we assign a certain width, W0, to all wires in a certain layer, they will all have the same resistance per unit length, R equal to Rs divided by W0. So here is an example where we are asked to estimate the sheet resistance of a 220 nanometer thick copper wire with a resistivity equal to 22 nano-ohmmeters. The sheet resistivity is given by resistivity ρ divided by thickness T, which is 0.1 ohms per square. So find the total resistance if the wire is 125 nanometers wide and 1 millimeter long. The resistance is given by the sheet resistivity, 0.1 ohm per square, multiplied with the number of squares, which in this case is 8,000. 1 millimeter divided by the 125 nanometers. That gives us a total resistance of 800 ohms. So wires 125 nanometer wide, they have a resistivity per unit length of 800 ohms per millimeter. Now let us turn our attention to wire capacitance. Wires, like the one highlighted in the middle of this figure, has capacitance per unit length to neighbors in the same layer, and to layers above, and to layers below. The parallel plate capacitances illustrated in this figure can be easily obtained from the well-known parallel plate capacitance equation, where the capacitance is given by the dielectric permittivity times the area of the parallel plates divided by the thickness of the dielectric. In the case of the top-bottom capacitances, the area is the width times the length of the wire. The dielectric constant, or the permittivity, is given by kappa of the material used times epsilon 0, which is the dielectric constant in vacuum. When silicon dioxide is used as the insulator, its permittivity is 4, but in the interconnect, very often low kappa materials with kappa less than 3 are being used. Okay, we have parallel plate capacitance, but to the parallel plate capacitance, we must also add fringing field capacitances. They are a little bit more complex to calculate, but here is a useful approximation where the wire is split into two. We have a circular wire with a diameter equal to the height of the wire, and there are formulas for circular wire capacitances, plus the bottom plate capacitance, where we have adjusted the width of the wire to compensate for that we already have some bottom plate capacitance here. As you certainly understand, the capacitance of a wire strongly depends on its environment, as is also shown in this right-hand graph, where the total capacitance is plotted versus the wire width. For two different cases, one case indicated by dashed lines is for an isolated wire, and another case indicated by solid lines, where the wire is between a metal 1 plane and a metal 3 plane. In both cases, the data is given for four different values of the spacing S between the wire and its surrounding wires. As we can see in the graph, for the isolated wire, it depends strongly on the spacing, but less on the wire width. On the other hand, for the wire between the metal 3 and the metal 1 planes, it strongly depends on the wire width, and somewhat less on the spacing. I tried to reproduce this data by applying the numbers given into the model in the previous slide, and I obtained somewhat results that are agreeing rather well with what is given in the graph, but there are also some discrepancies, so the model in the graph could be somewhat different from the one indicated on the previous slide. So what is the conclusion to draw from this slide? Well, a typical value for the wire capacitance is on the order of 200 attofarads per micron. That is 2.2 femtofarads per micron, or if you like 200 femtofarads per millimeter, value to be compared with the 1.2 femtofarads per micron for the MOSFET gate capacitances. So there is a factor of 6 difference between these two capacitances. To summarize so far, we have found that the RC product of a wire increases as the wire length squared. For our 1 mm example wire, the RC product was found to be 160 picoseconds because we had a wire resistant per unit length of 800 ohms per millimeter and a wire capacitance per unit length of 200 femtofarads per millimeter. In comparison to these 160 picoseconds, we can say that the RC time constant of an inverter with a fan out of 4 was previously found to be 36 picoseconds, corresponding to a fan out of 4 delay of 25 picoseconds. This slide shows some different views of modern interconnect. On the left-hand side, we can see a cross-sectional view of a 6 metal layer CMOS process with local tungsten interconnect at the bottom level and 6 copper metal layers on top of that. We can see that the bottom layers for local interconnect, they are thin and narrow, while metal layers for global interconnect are getting wider and thicker as we move upwards in the hierarchy. The right-hand side photos, they show some interconnect details after removal of the insulating material, separating the wires both within the specific layer and between the different layers. Now, let's have a look at wire delay scaling, starting with local wires. This slide shows two chips where the same functionality has been implemented in two different technology nodes. When the design to the left is moved to the next technology node, the chip area scales as 1 over s squared, where s is the geometry scaling factor. Typically, the new chip area is only about half of the previous one. For local wires, crossing the same amount of circuitry, the resistance stays roughly constant since the aspect ratio, L over W, does not change since length and width are scaled the same way. The sheet resistivity, Rs, does not change if the wire height stays large and/or we change the material to copper. The capacitance, it decreases by the scaling factor since the capacitance since unit length stays constant while the length is decreasing. Hence, wire delay tracks the gate delay and both scales as 1 over s. Now let's have a look at the delay scaling for global wires. This slide shows an example when advantage has been taken of the geometry scaling to add functionality to the design when it is moved to the next technology node, thereby keeping the chip area constant. This means that global wire lengths are not scaled, they are kept constant. So for global wires crossing the whole chip, the resistance grows linearly with the scaling factor instead of staying constant as it did in the previous case. The capacitance stays fixed instead of decreasing as it did in the previous case. The capacitance per unit length is still constant, but now also the wire length is constant. So thereby we see two opposite trends. The wire delay increases with the scaling factor, while the gate delay decreases. This slide contains a graph showing how the number of wires of different lengths have changed during the development of the Pentium processors across 4 different technology nodes. A careful look shows that there is an increasing number of shorter wires. That is, local wire length scales with the scaling factor of the technology. They are getting shorter and shorter. When it comes to global wires, we can see that they are getting longer and longer. Global wire length scales with the die size, which is getting larger and larger as more functionality is added. This graph shows the step response to a rising input voltage along a resistive wire as a function of time and wire length. Most obvious is that the rise time increases along the wire and must be restored by an inverter or logic gate at the wire end. So in the beginning of the wire, the signal is still very sharp as a function of time with a short rise time. But as we look further and further along the wire, this is at the half of the wire length, and this is at the end of the wire, and the rise time has increased considerably. So in summary, we have discussed the importance of accurate wire modeling, considering not only wire capacitance, but also wire resistance as wires get longer and skinnier. We have defined the concept of sheet resistance in ohms per square. We have had a look at typical on-chip wire length distributions, and we have had a look at wire capacitance depending on the surrounding wiring on top, below, and along the side walls of the wires. So, thanks for listening.